Hey guys, how's it going? As a follow-up to my gyroscopic eye and angular resolution videos, I wanted to simplify and illustrate a few applications of perspective and angular resolution in order to better understand why and how we see the way that we do. Now, we know that our eyesight is based on perspective and that there is a limit to our vision. This is why we cannot see to infinity, and we definitely cannot see across the ocean. So first, I just wanted to quickly recap how images are displayed in your eye, how perspective is constructed in your eye or any image-forming device. The light waves come into your eye and form an image on your retina. And remember, the image is created upside down because that's how the light enters your eye, and the size of the image is a function of the size of the angle. Larger and closer objects will form bigger angles, and therefore the image on your retina is bigger. Smaller or further objects will form smaller angles, and therefore the image on your retina is smaller. These angles allow us to use depth perception, judge sizes of objects, and also determine whether objects are coming toward us or moving away from us. Once an object is too small or too far away, the angle will become so small that it will go beyond our ability to see it, to resolve it in our eyes. And this is called going past the angular resolution limit of our eyesight. It's all about the angles. The angular resolution limit of human vision is about 1 arc minute, or 0.02 of a degree. And that 0.02 of a degree represents an angle. Once light comes in at a smaller angle, we cannot see it. The cells on our retina cannot resolve anything smaller than 0.02 of an angle. That is the absolute best we can do. That is the limit. We can do worse due to diffraction and other conditions, but never better. That is the physical limit of our eyesight due to the size of the cells on our retina and the size of our pupil. So I would like to start with perspective and how parallel objects seem to converge at the vanishing point or the horizon. We always throw around the word perspective, but we never seem to break down exactly how it is formed by our vision. Take the example of railroad tracks. Now, we know that they are parallel, and they always remain parallel. So how and why does perspective make them appear to converge, to meet at the vanishing point? The why is easy. It allows us to perceive distances, depth, and sizes. And the how is easy to understand as well, but we never really think about it. I want to demonstrate how this occurs, and it is due to the angles. Again, it is truly all about the angles. So, how do our eyes render the convergence of the railroad tracks? And to understand this, we need to look at the railroad tracks from a different vantage point. Let's look at them from above this time, from a bird's eye view, so that we can learn exactly how the tracks seem to converge at a vanishing point. Here, we are looking at train tracks from above, and this object here is supposed to be an eyeball. Bear with me, this is just to illustrate the concept of the angles and how they render the convergence. And remember, we are looking down from above like a bird's eye view. From this view, we can see how the tracks are parallel, but in the eyes of the observer on the tracks, they would appear to converge at a vanishing point. So, as the observer gazes out over the tracks, they seem to converge in the distance. To illustrate how the angles are formed in the eye, let's draw lines from the trusses into the eye and examine the size of the angles. The close truss forms quite a large angle, which means that it will form a large image on the retina. Now, notice how the truss a little further away forms a smaller angle, and accordingly the image on our retina will be smaller. As we draw lines from the trusses that are even further, notice how the angles get smaller and smaller. The angle determines the size of the image on your retina. A very simple concept, yet we take it for granted. Look at the angles formed in your eye. The close trusses form larger angles, and therefore these trusses are rendered larger in your eye. The further trusses form smaller angles, and therefore they are rendered smaller and smaller, just like in the perspective drawings. When the angle gets so small that it is smaller than the limits of our eyesight, the truss or any object will disappear, will vanish at the vanishing point. So the bird's eye view allows us to see how the angles determine the size of objects in your vision. Now let's look at a side view, and this will allow us to see how the items are displayed in relation to the horizon. In this sideways picture, the dotted line represents eye level or the horizon. So I'm going to draw a straight line from each truss, and as you see, due to the angles, the near truss is rendered at the bottom or foreground of the perspective drawing, and it appears at the top of the eye, but again the image is flipped, so the close truss is rendered at the bottom of the perspective drawing or the top of your eye. And as we draw lines from the further trusses, we see how the angles cause them to be displayed closer to the horizon or the eye level line. So the furthest trusses, as they are vanishing, are also approaching the horizon line in your eye. Simply put, the angle is based on the distance from the observer, and the angle determines where the object is displayed in relation to the horizon. Larger angle, further from the horizon. Smaller angle, closer to the horizon or vanishing point. So let's look at each truss as it appears in each view. This truss in the foreground is the same as this truss and is finally displayed like this in your vision. This is what you see. This truss in the middle is the same as this truss, and it is finally displayed like this in your vision. And the further truss is the same as this truss, and it is finally displayed like this. So you see, the angles determine the size of the object in your vision and the position of the object in your vision. And all of the angles together create the effect of perspective. So we see from the bird's eye view of the railroad tracks how angles determine how objects are displayed in our eye. Now let's look at the horizon, and this time let's look at it from a side view. This will allow us to visualize, although not to scale, how angular resolution works to form the horizon. Now, before I develop this further, I must illustrate what is happening in our eye with regard to the horizon. In our eye, let's consider where the horizon would be rendered, a midway area that is the exact eye level plane. Think of the receptor cells on our retina as pixels, and the imaginary eye level line is between a row of pixels. The slightest tick downward, which is necessary if we want to see the ground, would look something like this. And the slightest tick upward, if we want to see the sky, would look something like this. Now, when this happens, you are seeing a flat, straight line cut across your retina. This is your horizon, and it is simply where everything you can see above eye level meets with everything you can see below your eye level. To you is a straight line, a crisp line. After all, we are talking about tiny pixels or retina cells, but that is what represents your horizon. That is your horizon. These angles are minuscule in your retina, and you can see how in your eye they seem to converge or meet because they are just a few pixels or receptor cells apart. However, if you were to extend these lines or light waves out to the limits above and below, in reality the sky and ground are thousands of miles apart. It's truly amazing. So to illustrate this further, let's look at this picture, and the dotted line represents this stick figure's eye level. To confirm this 3-mile horizon, we can actually take the eye level and then make the smallest angle of declination toward the ground that our eye can resolve, and remember that's 0.02. Obviously at eye level we are never going to see the ground, so we have to use the smallest angle of declination that our eye can handle. If you make right triangles out of this, you can plug in the person's height and the angle of 0.02 to figure out the distance. Now, as a rectangle, this angle will be equal to this angle, and so let's take these values and put them into the right angle triangle calculator to see how far this base section is. We put in 6 for side A and then 0.02 for angle A, which is our angular resolution limit, and we come up with 17,200 for the base, and when we divide that by 5,280 feet per mile, we get 3.25 miles. There it is. We have the distance to the horizon, which is due to the angular resolution limit of our eyesight, not a magical ball cliff that ships are going over. And this angular resolution limit of approximately 0.02 is the resolving power of your eye, and it is also the limit beyond which the light waves will diffract because the angle is too small. The light wave will bounce off the water on its way to your eye, and basically it will blur and mirror. This is why you see the mirroring or inferior mirage effect on the water or on roads, as the light waves are approaching the limit of angular resolution. Beyond the blur or mirror part, nothing is visible at all. They have completely gone beyond the limit of your vision. Now, the ground is easy. The tricky part comes when we consider what happens above our eye level. Here, the same angular resolution limit applies, but since there is so much more area, distance, and atmosphere, diffraction also plays a big part. Remember, angular resolution is the fixed limit. Your visual acuity can be much worse than this limit, but it can never be better. This is a physical limitation based on the size of your receptor cells, pupils, and the wavelengths of light. And Rob Skiba in his videos showed perfectly how diffraction and atmospheric lensing affect our eyesight as well and are a contributing factor. So, as our eye resolves everything above our eye level, it reaches a fixed limit, this time at the ceiling. By the time this angle that I've drawn above the man's eye level reaches the celestial plane of the sun, moon, and stars, it is somewhere around 7,000 miles if we were to go along the ground, and the exact distance is not important right now. The important thing to note is that there is a fixed limit based on angles. I use 7,000 because at sunrise here in Florida, the sun is directly over West Africa, which is about 7,000 miles away. So to visualize what is happening, I created this page, and this line represents the extension of that teeny tiny angle from our eye level when it finally reaches the celestial plane. So what happens when the sun comes into or goes out of this limit? This is how you get the sunrise and sunset. Now, in your eye, perspective makes it seem like it is at your eye level. That is because, for all intents and purposes, it is at your eye level. And that is why the sun appears to rise and set at the horizon in your eye. What is happening is that it is simply coming into the angular resolution limit of your eyesight. You see the sun at the sharpest angle possible from eye level. When the sun gets within a certain distance to your position, the light waves can finally make it into your eye at an angle that can be resolved. Before that time, the angles are just too small. The light will diffract or not be visible at all. And again, it is simply a function of perspective and angular resolution with the additional factor of diffraction or atmospheric lensing. However, the fixed physical limit is what will always determine when sunsets and sunrises occur. And so check this out. Look how the sun comes into and goes out of the angular resolution limit of our eyes. And then this is what it looks like from our perspective when we are actually viewing it in real life. Pretty cool how it works, at least in my opinion. So, hopefully this was helpful to better understand how perspective and angular resolution determine our vision. Thanks so much for watching. Have a good day. Adios.